All right, let's jump right in. Today we're tackling a topic that pretty much every software developer has heard of, but let's be honest, often struggles to really apply in the real world. I'm talking about the solid principles. You know that feeling, right? That sinking feeling when you make one tiny change over here and a whole bunch of unrelated things break over there. It's like playing a game of Jenga with your codebase. That fragility, that fear of touching anything, that's exactly the problem we're going to talk about solving. And this quote just hits the nail on the head. For a lot of us, solid feels, well, a bit academic, like a rigid set of rules you have to memorize. But it's so much more than that. So let's get past the textbook definitions and build a real, practical understanding of what these principles are all about. So SOLID, it's an acronym, of course, for 5 design concepts introduced by the legendary Robert C. Martin, or Uncle Bob. But here is the most important thing to get right from the start. These are not commandments etched in stone. Seriously. Think of them more like a design philosophy, a mental toolkit to help you write software that doesn't crumble the second you need to change or grow it. Okay, first up, the S, the single responsibility principle. And listen closely, because this is where a lot of people get tripped up. It's not just about a class doing one thing. The real insight here is about having only one reason to change. What does that mean? It means a class should be responsible to one and only one business actor or concern. Let's make this real. Imagine you have a student class. Should that class also know how to save itself to a database and maybe send a confirmation email? No way. Think about it. If the finance department wants a change in how reports are structured, why on earth should that risk breaking the email system for new student signups? By lumping them together, you create this tangled mess. Splitting them up, now that's clean. So the big win here? It's all about isolating change. A business rule changes, you change one module. That's it. You dramatically lower the risk of side effects. It's a huge deal for maintainability. Okay, that's S. Now let's move on to O, because these principles really build on each other. All right, the O stands for the open/closed principle. Now at first, this sounds completely contradictory, right? Open for extension, but closed for modification? What? But it's actually genius. It means you should be able to add new features without ever touching the old, battle-tested code that you know already works. So, instead of cracking open a perfectly good class and slapping in another if-else block every time a new feature is requested, you find a way to extend it from the outside. You can use patterns like decorators, composition, or even simple plugins. The point is, you're adding on, not performing surgery on a healthy patient. You leave the core, working code alone. And the payoff here is massive. You're not breaking your existing unit tests. You're not introducing weird bugs into code that was perfectly fine 5 minutes ago. Your codebase stays stable, and you can add features with confidence, not fear. Okay, on to the L, the Liskov substitution principle. I know, it's a mouthful. It's named after the brilliant computer scientist Barbara Liskov. This one can feel a bit academic, but trust me, the core idea is super practical. It's all about making sure our inheritance hierarchies actually make sense. This example just nails it. Let's say you have a parent class, and a child class inherits from it. Well, a parent can go to work. Can a child do that? Nope. So if your code expects a parent object, but you pass it a child object instead, it's going to break when it tries to call go to work. That's a violation. It means your abstraction is wrong. You can't just substitute one for the other. The better solution is a more general-base class, like human. And why does this matter so much? Because when you get this wrong, you end up with fragile, brittle code full of weird checks and unexpected runtime bugs that are a nightmare to track down. Getting LSP right is what makes polymorphism actually powerful and reliable. Next up, let's talk about I, the interface segregation principle. The simplest way to think about this is don't create fat interfaces. You know, those giant interfaces with dozens of methods? The goal is to prefer many small specific interfaces over one big one that does everything. A classic case is a data repository. You might have one big interface with methods to create, read, update, and delete. But what if you have a component that only ever reads data? Why should it be forced to depend on methods for deleting and updating that it will never ever use? It's just unnecessary baggage. By splitting that big interface into smaller ones like iReadable repository and iWritable repository, your system becomes way more flexible.
Your components can now depend only on the exact functionality they need, which makes everything more modular and loosely coupled.
And that brings us to our final letter, D, for the dependency inversion principle. Okay, this one is a true game changer. It's probably the most powerful of the 5, and it's really at the heart of almost all modern software architecture. It's all about flipping dependencies on their head. So here's the typical flow. Your high-level business logic, say a billing service, directly knows about and depends on a low-level SQL database class. Dependency inversion flips that script. It says, no, no, no. The high-level billing service shouldn't depend on a concrete database. Instead, both of them should depend on an abstraction, like an iBilling repository interface. The dependency is inverted. What's the immediate massive win here? Testing. It becomes a breeze. Now for your unit tests, you can just create a fake, in-memory version of that repository and inject it. No more spinning up a real database just to test your business logic. This makes your tests lightning fast and super reliable.
Now, it's super important to see how these 5 principles aren't just separate rules. They work together like a team. SRP gives you the focus building blocks. OCP lets you add to them without breaking them. LSP makes sure your abstractions are solid. ISP keeps the connections clean. And finally, DIP wires the whole thing together, making your system scalable and decoupled.
But we also have to be realistic. Principles can sometimes clash. Take the famous don't repeat yourself or DRY principle. If you follow it too religiously, you might combine 2 totally unrelated things just because they happen to share a few lines of code. And in doing so, you could accidentally violate the single responsibility principle by coupling them together. It's always a balancing act. And this brings me to maybe the most important point of all. Solid is a tool, not a religion. It is not the goal. If you apply every single one of these principles to a simple throwaway script, you're going to create a monstrously over-engineered mess. The key is to apply them pragmatically as the needs of your project grow.
So, where do these principles really pay off? Big time. They shine in large code bases, on systems that are meant to live for years, and especially on teams where lots of developers are working together. For that quick and dirty prototype you need by tomorrow, yeah, it's probably overkill. Context, as always, is king.
So how can you make this practical? Here's the takeaway. Turn the principles into a mental checklist. As you're coding, just ask yourself these simple questions. Does this have more than one reason to change? Am I going to have to tear this open later to add something? Is this interface getting too fat? When you start thinking like this, Solid stops being some abstract concept and starts being a powerful, practical guide for your day-to-day work. Because here's the thing. The real goal isn't just to follow the rules. Anyone can do that. The real challenge, and the mark of a truly experienced engineer, is knowing when and why to bend or even break them. It's about understanding the trade-offs and making smart, informed decisions for the problem you're actually trying to solve. And that is a much more powerful skill than just memorizing an acronym.